Hello everyone. Today I am going to present the paper Fast Variance Reduction Method with Stochastic Path Size. In this paper, we will study a framework of variance reduction methods with randomized path size and introduce the new algorithm called Saga++ that has an improvement in terms of running time, the need for conversion compared to Saga. The presentation going to go through six sessions. Introduction, Saga method, introduction of a new framework for variance reduction with stochastic path size, conversion analysis, introduce new algorithm Saga++, and final is the experimental results. Traditional method for optimization is gradient descent. With gradient descent, it yields on data for one update, so it has low variance with high conversion rate. But in large-scale application, when number of training samples become very big, this method is used with high computation cost per iteration. Stochastic gradient descent appears to solve this problem. Stochastic gradient descent only yields path size equal to 1, so it has low computation cost per iteration in the trade-off with low conversion rate due to high variance. People need more. A family of variance reduction methods were invented to get better conversion rate by using reverse derivative information for reduce the variance while keep working with path size equal to 1. SIG, Saga, HVRG is the candidate of this family. Please note that Saga is variance reduction method. We will mention about this method later. This paper proposes a framework with stochastic path size based on Saga method. Instead of using path size equal to 1, it randomized path size follows some distribution for each iteration. It also proposes new algorithm Saga++ that randomized path size follow the rule. For each iteration, probability of path size equal to n e p and probability of path size equal to 1 e 1 minus p. Saga++ so that it can improve the conversion speed in terms of running time. Here, Saga is the base algorithm, so let's have a quick look on that. Saga is a method to solve the following finite sum composite optimization problem. Here, fi is a loss function for each training sample, n is the number of training samples that you have, g is the regularization term. Saga yield path size 1 and store on more present node derivative fi frame, that is the reverse gradient, evaluated on sample si. And let it contribute to the learning rule by sum average on of them. Variance reduced gradient is calculated by sum difference between new derivative term and our derivative term plus u bar. Learning rule is updated with proximal operator due to the presence of regularization term G here. Based on Saga, they propose the framework variance reduction with stochastic backside. The difference here is for each iteration, backside is randomized, follow some distribution and corresponding variance reduced gradient vector. Instead, take average sum of the new derivative term minus average sum of all derivative rule on chosen sample. Put this into the complete algorithm. We get this. Here we have n training sample and initial check W0. We want to find W that minimize f function. For each iteration, we choose a backside randomly based on some distribution. Then we sample a backside. We sample a path that has the backside equal to b. Calculated variance reduce variance vector and update W. Update the random memory by the new derivative term and update the u-bar. Let's do some conversion analysis for this framework. Assume that the objective function is mu strongly convex and L elliptic smooth. Condition number is calculated by L over mu. Then, if you choose the learning rate equal to this term, learning rate is based on the expectation of the backside here. Our algorithm will convert linearly with a contraction factor 1 minus rho. Here, rho is equal to gamma times mu. And this gamma is optimal in terms of conversion rate. In terms of minimizing number of data access, the optimal of backside can be calculated by this term. The function here is monotone increasing with expectation of backside. So theoretically, the backside should be 1. So if you choose backside 1, the previous framework is useless because it uses random backside. In practice, the case disk I/O affects the running time. We call conversion speed. The intuition is that the running time for sequential data access is less than random data access. We can see the result here. So, in real backside can help in terms of running time. So, our Bow framework help in this situation, and Saga++ is propose. Saga++ based on variance reduction with stochastic backside framework and propose the rule for randomizing backside that is at each time step the probability of backside is equal to n EP, otherwise backside is equal to 1. The relationship between conditional number and optimal backside and eta here is shown in the graph, where eta is the proportion of time for sequential access per time for random access. If condition number is big, batch size should be small, and vice versa. If uh, eta is small, batch size should be big, and vice versa. Experimental results in terms of data access show that Saga++ yellow line is larger than Saga green line. But in terms of running time, Saga++ is the best. The experimental result from KDDP dataset with different hyperparameter lambda and between datasets also show that Saga++ yellow line is the best in terms of running time. Thank you for your attention.